Hello there, virtual Earth and Space Science. So we're starting to learn about stars now, and at the beginning of that we're going to talk about the structure of stars, what goes on inside a star. And stars are surprisingly simple things. They're big balls of hot ionized gas. Ionized means that the atoms in these stars are so hot that the electrons have been stripped right off of them, and so we have bare electrons and nuclei running around inside an ionized gas. But a gas like this can be specified by three physical properties or parameters: temperature, pressure, and density. Now I know these words should sound familiar to you, and you've probably learned about them in a science class somewhere recently, but I figure a review wouldn't hurt. So the first one is temperature. Temperature really measures how much energy the particles, or the atoms, the electrons, and nuclei in a star have. Temperature measures the average kinetic energy of all the particles. And just to give you a visual, on the left we have a low temperature gas where the atoms are barely moving, and on the right we have a high temperature gas where the atoms are moving much more quickly. Okay, so low temperature, slow atoms. High temperature, fast atoms. And that's the idea of what's going on the atomic scale with temperature. The second important parameter is pressure. Pressure essentially measures the force, it's really the force per square meter, the force caused by these moving particles. High pressure and low pressure, well, a high pressure gas, the particles are going to exert more force on any surface that they encounter, and a low pressure gas, they're going to exert less force. As you might expect, temperature and pressure are related. When a gas gets hotter, it's going to normally exert more pressure on any surface that it encounters, and when it's cooler it exerts less. There's a nice visual on the website that I asked you to look at. I think it's on section 7, that shows you a hot gas and a cool gas and how a hot gas exerts more pressure. So that's an important thing to keep in mind. When a gas heats up, it exerts more pressure and it tends to expand, it tends to puff up. When a gas cools down, it exerts less pressure and it tends to shrink. Think about a balloon on a cold day. On a cold day, a balloon tends to shrink and lose some of its volume. The third important variable here is the mass density. The mass density is really just how many particles you can shove into a cubic centimeter. High density would look like this, and low density would look like this. These three things, temperature, pressure, and density, are all related by a mathematical equation called the equation of state. We're not really going to mess with the math on that very much, but they are related to each other, and we're going to talk about those relationships qualitatively, if not quantitatively. We'll start out by exploring just what it is that keeps a star together, that makes it keep its nice, round, stable shape for so long. And it's called hydrostatic equilibrium. It's what holds the sun together, it's what holds all stars together, it's what keeps the Earth's atmosphere the nice way that it is. Hydrostatic equilibrium. Static meaning not moving. The sun is not shrinking or expanding, at least not much. And equilibrium meaning balanced. And the two forces at work here, or the two things at work that keep the sun in balance, are gravity. Gravity is sort of a silent assassin out there, always trying to pull everything together. It's trying to crush the sun into a smaller star because of the mass inside the sun pulling on all the other mass. So gravity is fighting against pressure. The force and the energy of those molecules and atoms and ions inside the sun act to expand the sun and try to make it larger. And so the balance between these two things is what keeps the sun at the size that it is. It also does some other important and interesting things. Hydrostatic equilibrium is responsible for making the sun round. If any part of the sun were to stick out more than any other, to depart from that round spherical shape, the gravity on it would act stronger than the pressure on it and pull it back down so that it would be round like the rest. If any part of the sun were to be pushed in more than the rest, the pressure would act stronger than the gravity and correct that deformity as well. And so these forces balance out to give this perfect round shape. The Earth is also round for a similar reason. Any object that's sufficiently massive will be round. Asteroids that are below a certain mass threshold can be kind of funky wonky shaped and not round, but most objects of a certain size, the Earth is certainly big enough, are round because of the hydrostatic equilibrium, the gravity and the pressure balancing out. Hydrostatic equilibrium can also be used to explain some other interesting things. The deeper you go into a star, the denser it gets and the hotter it gets. And this is because the deeper down you go, the more stuff is piled on top of you, right? If you live near the center of the sun, you'd have all sorts of stuff pushing down on you because of gravity. So the reaction that the gas has towards that is that it becomes denser, it becomes more compacted and compressed. And also, it has to become hotter. If it didn't become hotter, it wouldn't be able to provide enough pressure to resist all that squeezing from the outer layers. So, the inner part of a star is denser and hotter and has higher pressure than the outer part of a star. Because of this, it's the inner part of a star where fusion happens. Because if you remember when we talked about the sun, in order to make fusion start, which is the power source of the sun, you have to have very high densities and temperatures and pressures. And those are only available on the inside of a star. Finally, this hydrostatic equilibrium causes the sun to be very stable. It regulates the fusion rate inside the center of the sun. If the sun were to, say, have a little burp and start to do fusion too fast, it would provide more temperature and therefore more pressure, and it would cause the sun to expand a little bit and become slightly larger. And when it expands, it would cool off, because in expanding, it would release some of the pressure. If the sun started to slow down in its fusion rate, then it would produce less temperature and pressure on the inside, and it would therefore contract. Gravity would start to win, and it would contract, and when it contracts, it would heat up, because that contracting would cause the fusion inside to happen faster. So it's kind of neat. It's kind of like a thermostat, a regulation, a stability factor. If the sun starts to fuse too fast, it expands and the fusion slows down. If it starts to fuse too slowly, it contracts and fusion speeds back up again. So this keeps the fusion at a very steady rate. This steady output of energy from the sun has made it possible for life to evolve on Earth for billions of years. So it's good news for us that our sun has this nice built-in stability mechanism. Hydrostatic equilibrium can also help us to understand the relationship between luminosity and mass. Stars have these two properties, luminosity and mass. The luminosity is essentially how bright the star is, how much energy it puts out, and the mass is essentially how heavy the star is, how big is it. It turns out that the luminosity depends very heavily on the mass. We're going to learn more about this soon when we talk about different types of stars. The luminosity is proportional to the mass to the third power or the fourth power. It's kind of in between. For an example to illustrate this, a star that was twice as massive as the sun would have a luminosity, meaning a brightness, of 8 to 16 times the sun's luminosity. 2 to the third would be 8, 2 to the fourth would be 16. Anyway, something like 10 times as bright, with just twice the mass. So mass is probably the most important property of a star. A star that was 10 times the mass of the sun would have a luminosity of several thousand times the luminosity of the sun. We wouldn't even be able to get near that thing before it just totally fried us. So, when we talk more about this later, I want you to remember back to hydrostatic equilibrium. A more massive star is going to have much more gravity pushing in on it, right? And if it has much more gravity pushing in on it, the central part of that star is going to be very, very, very dense, hot, and under high pressure. And that's going to cause fusion to happen there very quickly. That high rate of fusion is going to produce tons and tons of energy, and this star is going to be super duper bright. So again, that idea of gravity balancing pressure, causing hydrostatic equilibrium, helps us to explain this relationship between luminosity and mass. Pretty cool, huh? Alright, so go check out sections 7, 8, and 9 and try to answer the questions there.